This is the 4.1 to 4.2 review. Calculators are not allowed, and the upshot of the problem is we want to find the value of c that satisfies the conclusion of the mean value theorem. So the conclusion, if you recall, says that the tangent slope has to equal the secant slope for some value of c in the open interval from a to b. So our job is to figure out what a is, what b is, compute the secant slope, find the tangent slope and plug c in, and then figure out when those two things are equal. So we have three different kinds of problems. We've got an exponential, a polynomial, and a trig. But the process is going to be the same for all three of them. For all three, we need to find the tangent slope at c, we need to compute the secant slope, and we need to set them equal. So if we look at part A, we're going to need our tangent slope, which is the derivative of this function. So we do the chain rule, e to the 2x minus 4 times a 2. And then we're also going to need f of b, which is this f with the 3 plugged in, which would be e to the 6 minus 4, which is e squared. And then we also need our f of a, which is f of 2, which would be e to the 4 minus 4, which is e to the 0, or 1. So now we're ready to set up our expression here for the conclusion of the MVT, and that will be f prime of c, which is 2e to the 2c minus 4, has to equal f of b minus f of a over b minus a. If we simplify this now, we'll get 2e to the 2c minus 4 equals an e squared minus 1. In order to get e isolated, we're going to need to move the 2 and the the c isolated. We need to move the 2 and the e and the 4 and the 2. So we can systematically strip everything off. We'll have e to the 2c minus 4 equals a 1/2 e squared minus a 1/2. Then we can log both sides. So that would be the 2c minus 4 will be the log natural of, I think I'm going to leave it like this because that's how it's written in my answer key, instead of distributing that half all the way through. Then I need to add 4. And then I need to divide by 2. Now in this case I think I did distribute the half, so I had a half of the log natural of an e squared minus 1 over 2 plus a 2. So there is my c value. Since I only found one, I can assume that the one I found is in that open interval. So you could, if you wanted, to figure out what that is and confirm that it's between 2 and 3, but since there's only one and the MVT requires that we'll have at least one, we can probably stop there. Okay, so let's look at part B. Part B is a polynomial, so again we're going to need our derivative, which is a 12x squared minus 2. We need to know our f of 2, which is our f of our b. We plug 2 in and we get a 32 minus 4 plus a 2 gives me a 30. And we need an f of 0, which is going to be 2. So now that we have our derivative and our f of b, our f of a, we can set up our equation, which will be f prime of c, which is a 12c squared minus 2, has to equal f of b minus f of a over b minus a. So that'll give me a 12c squared minus 2 equals a 28 over 2, which is 14. So if I add 2 to both sides and then divide by 12 and reduce, now in order to find the c, I need to take the square root. And when you introduce the square root, you have to put a plus or minus on it. So square root of 4/3 is the same as plus or minus 2 over root 3, and if you rationalize the denominator, it's a 2 root 3 over 3. Now looking at this, I have a positive and a negative, but my open interval would be from a to b, which is only positive values. So that means the only c I get to keep is the positive one, because that's the one guaranteed by the MVT. My final one, part C, is the trig version. So I have f of x equals 2 times the sine of 3x. So with that one, I'm going to need my derivative. Move through the 2, hit the sign, hit the inside, and I'm going to need my f of b, which if I go all the way back up here, my b is a pi over 3, and my a is a negative pi over 3. So coming back down here, if I plug a pi over 3 in for x, that'll be the sine of a pi times 2. Well, that's just 0. If I plug in a negative pi over 3 and multiply by 3, that's the sine of a negative pi, which is also 0. So we can see now that our f prime of c, which is our derivative with the c plugged in, needs to equal f of b minus f of a over b minus a. Well, since it's 0 minus 0 on top, we're just going to end up with a 0. So we're interested in knowing, when does a cosine equal 0? Well, cosines equal 0 anytime the x-coordinate on the unit circle is 0. So we can go around that circle a whole lot of times. We could go positive pi over 2, positive 3 pi over 2, 5 pi over 2, 7 pi over 2, and I could keep going around counterclockwise. Or I can go the other way and get a negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, etc., etc. So we know as long as the inside of the cosine equals any of those values, then the cosine will end up being 0. So our job is to now solve for c, because this will go on and on. If I want to solve for c, that means I need to divide by a 3. So I'll get c equals plus or minus pi over 6, plus or minus pi over 2, plus or minus 5 pi over 6, etc., etc. Now, there are an infinite number of these. My job is to find the ones that are in between negative pi over 3 and positive pi over 3. Well, pi over 2 is already outside the interval, as is negative pi over 2, so we're not going to use any of these ones. We're actually only going to have the plus or minus pi over 6 guaranteed to us by the mean value theorem.